Okay, so we're going to talk about volumes of solids of known cross-section and volumes of solids of revolution. That's the next stage here. The first part of this lesson will be the volumes of solids with known cross-sections. So I have a couple things drawn here. I'm going to erase this part here for now. But, and I might erase this here too. Okay, so let's just take a look at this cube, okay? Yeah, I'll erase all this. Let's take a look at this cube. Right here. If we wanted to find the volume of this cube, geometrically or algebraically, whatever, the volume would be A times A times A, right? That would be the area of the base, is generally what we've been taught, times the height gives us the entire volume, okay? So that's something that we know and is pretty straightforward. Another way you could think of it is, think of it sideways. Just turn that cube sideways. And if you think about it like this, the area of one side, right, times, and when we say multiply, we multiply it by a third dimension of depth. That also gives us the volume, right? It'd still be A times A times A. Well, what if we had, and I draw the second picture here. I have the second diagram here. And that's the same sort of thing that we're talking about. So if we have a slice of an area on one side, and then we multiply it by the depth. In essence, what we're doing is we're multiplying, or we're really adding a whole bunch of little cross sections together, right? For the number of units that the depth is. So that's what that third dimension is. Well, in calculus, we could think of that a different way, right? We can think of that as, let's take the area of this and let's multiply this by some narrow width, right? So we could have, oh, that's getting a little wonky there. We could have the area of one of the sides, that's even worse, times, oh, what is going on? My tile is crooked here. Sorry, times the width here, right? And that would be really the area of this edge, this side, times some small little change. And if we let this be the x-axis, and this was the y-axis, right, x and y, then this would be the area times some little differential in x there, right? And if we added up a whole bunch of these, and if this little differential in x became 0, then we would have an infinite number of these things we would be adding up. So you could think about this, the area of this one slice, when you multiply it by the length here, or this third dimension, you could think about it as adding up an infinite number of slices of this area that's on the side, right? So it would be the area, and if we could write this area function here of this side, and we added all these up, it's kind of turns into this, right? Kind of turns into a bit of an integral, and where we find the area, what would be sort of underneath this top function here, if you want to call it that way, but would have the same depth as this height. And so it would be the area of this times a little section, and we do that an infinite number of times, and we get the area of our cube. So this is the beginning to this whole finding the volumes of solids of known cross-sections. So there's a cross-section that we know, it's a square, and we're multiplying it by a little differential in x, and so that differential is like a dx. And so really we're talking about an integral from, let's say this is now a to b, like it is on this diagram over here. You're looking for that integral from a to b. Okay? So again, we can think about it in terms of integrals. So here's the definition of a volume of a solid with a known cross-sectional area here. And this is from your Finney textbooks. I don't know if you have that handy. You can look up, it's chapter 7, exactly what page this is on. But it says this: the volume of a solid of known integrable cross-sectional area, A of x, from x to a to x to b, is the integral of a from a to b. So here is the area of the cross-section. And that cross-section could be a square, a times a, or the function height times itself. It could be a triangle, it could be a semicircle. We're going to look at all those today. So here's the area, here's the width, and we're taking the integral from, a to b. And that would be, as far as we often start at 0 and we go to some number and we can find that area. Okay? So the nice thing about this is that we can look at curves that aren't straight along the top. And we could do the same thing, really. We could find if this is f of x, right, the height here, and we wanted to add up this figure that looks like it has squares that match the height of the function. Even if the function changes height, we could find this little three-dimensional thing. So here's the radius, or the height here is pretty small, so this square is going to be small. Here the function height is pretty tall, so that is going to be tall. So you see how when these things vary in length, the value of this function becomes really important. And this would be f of x by f of x wherever you went. And so the value of the integral here, the importance of the integral, becomes apparent. All right, so let's take a look at this right here, and I'm just going to get rid of some of this as well. Okay, so this is what we're starting with here, and there we go. Can bring that in. You see that on the side. Okay, so this is kind of what we're looking at. Can we find the area of this pyramid? And I'm just going to bring that pyramid over a little bit. And maybe I'll make it a bit bigger. Can we find the area, or the volume of this pyramid? So the volume. So the neat thing about this is that the cross sections, if we were to slice that, the cross sections are squares, aren't they? Because it's a square-based pyramid. So we have a big square of 3 by 3 here. You see that? It's 3 by 3 on the very end. Halfway, it would be 1.5 by 1.5. A third of the way would be 1 by 1. At 0, the square that's at the very tip is 0 by 0, technically. Okay, so you can see that something's happening here. Okay, so the function really would be y equals x, and as x grows, so does y. And so you see we have all of these, if you can envision this, all of these little squares, right, of varying sizes, getting smaller as we get closer to the tip, getting larger as we get closer to the end. So do you guys remember at all in math classes previous sort of what the formula for the volume of a pyramid was? And let's draw the pyramid sort of on its side like this. So kind of a normal view of it. Do you guys remember what the volume was? Anybody? No? Ooh. All right. 1/3 the area of the base times the height. So whatever the area of that base is, you multiply it by the height, the overall height, and then you divide it by 3. So it would be 1/3 of the comparable prism volume. Okay, prism with the same base and top. So what would be, if we go from our just from our formula here, what would be the volume of this pyramid? It's on its side, but we have a base of 3 by 3, right? And a height of what? What's the height? Well, the height is 3 as well. So we'd have 1/3, 3 squared times 3. And that's going to be 9 units cubed. So this pyramid right here should be 9 units cubed. Does that make sense? Okay. So that's how we would find that sort of, traditionally, same thing we've done in math classes previous. Let's think about it in terms now of integrals, okay, and of calculus. Let's see if we can figure out how to add up an infinite number of squares that would make up this pyramid. And again, we want to look at it sort of sideways here like this, right? And we want to say, okay, the differential is x. The limits of integration are from 0 to 3, so 0 to 3. we're going to find the area of the cross sections, which we know is going to be what? Well, they're squares, so they're going to be x by x, right? So this is going to be x squared. And we're multiplying by the very small differential in x that represents that little tiny width, right? Which is almost infinitesimally small, right? So it's almost like it's a real two-dimensional area, really, and we're adding an infinite number of them, okay? So this is the integral that we want to set up, and we're going to compare to, the volume of the pyramid like we've found in the past. So if we were to do this, what's the antiderivative of x squared? 1/3 x cubed. Very good. So we're going to evaluate that from 0 to 3. So that's going to be 1/3 3 cubed minus 1/3 0 cubed. Okay. So 1/3 3 cubed, well, 3 cubed is 27. A third of that is 9. So we get our volume as 9 units cubed. See that? So, kind of neat. If you can wrap your head around this, a pyramid has cross sections, if you slice it up this way, of squares. So this is the area of the cross section. If you set the integral part up with the limits of integration being really equivalent to the height of the pyramid, then we can find its volume. Any questions about that example? So we're going to be using a handout created by Mark Sparks back in 2012. So just a shout out to Mark Sparks. You can look him up on YouTube and online there to support him. He's got some kind of really good stuff there, and I like the pictures, and I like sort of the summaries and the work here. So let's take a look at this. So cross sections that are squares. So if you can see that, this is sort of what we were doing with the pyramid, right? Except the pyramid was not shaped like this. It wasn't the containment of two separate functions. Well, if you think about that y equals x function we kind of had there, right? That's something sort of similar to, hey, there's a y equals x function, y equals negative x function, and could we do something there? So this is explaining how we can find the volumes of something like this with square cross sections in between two graphs, and we can find this by subtracting the upper graph. So f of x is going to be the graph on the top here, and g of x, you can't see that's just off there, but g of x is the bottom one, okay? So if you take the difference, f of x minus g of x, that's going to be the side length of one of the squares, okay? So if we were to find the area of the square that's in between f of x and g of x, the area is going to look like this. It's going to look like f of x minus g of x times itself, right? Because both dimensions would be the same. It's going to be a square. Or area is f of x minus g of x squared. If all of these cross-sectional areas, and again it's going to vary because the difference between the two functions vary as you move along from x equals 0 to x equals whatever this is going to be, but they're going to change. So if we wanted to add up all of the different size of squares, right? I didn't leave myself a lot of room, but that's going to be equal to this. It's going to be now a volume, and it's going to be the integral from a to b of f of x minus g of x all squared dx. So there's your integral representation. All right. So if the cross sections now are not squares, okay, they can be anything, right? They can be squares, they can be triangles, they can be equilateral triangles, they can be semicircles, they could be anything. So the rest of these next kind of page and a half here is talking about what happens if we were looking for something like this with the cross sections were triangles. And obviously that would give us a different looking three-dimensional solid, right? But you could find that out. All you have to do is find out what the area of one little slice would be in between those two functions. So the area of the triangle, of this triangle above, if it's a right triangle like this, you see, you'd have the difference between f of x minus g of x as the height and as the base. So the area here, the area for this is going to be 1/2 times the base, which is f of x minus g of x. 1/2 the base times the height. And the height is going to be the exact same thing. And hopefully you kind of see that this triangle here is the equivalent to half of this square, right? So it turns out to be just half. Okay. All right, so I'm going to give you guys a minute or two. I want you to fill out, actually we didn't do this one, sorry. So if we were to add up all of these cross-sectional areas, the volume is going to be, again, the integral from a to b of, now the 1/2 is a constant, so you can put it inside or you can put it outside. Probably outside of the integral would be best. From a to b of, here we go, f of x minus g of x, all squared dx. So now with that pattern, okay, I want you to do these two. These two may be a bit trickier. You got to find the area of this, and all you're given is this length right here. So you have to find the height. Okay? So take a couple minutes. I'm going to go help the group in the back there. They're working on something different. So you guys work on this, and I will come back to you in a few minutes and see if you can get these next two sections. Okay, so having problems finding the height. You want this right here, okay? That's going to be a right triangle there now. This also is f of x minus g of x, because it's equilateral, right? So if we do this work over here, really, you've got a squared plus b squared equals c squared now with this right triangle. Your a would be 1/2, right? F of x minus g of x. And that's going to be all squared. Plus the b is the height, so we don't know. And then this is f of x minus g of x, all squared, right? Okay. So b squared is going to be f of x minus g of x, all squared, minus, this is going to be really, I guess, 1/4 f of x minus g of x squared. Okay. So what do we end up with here? So if this is 1, right, and you're subtracting 1/4 of the same thing, let's see, this looks like 3/4 now, right, of f of x minus g of x, all squared. So if we take the square root of both sides, we end up with our height, which is going to be, what? Root 3 over 2 f of x minus g of x. As a height, you good with that? Or let's make that an h now, the height. Okay. So then the area is going to be 1/2 the base, which we know is f of x minus g of x, times the height, which is root 3 over 2 f of x minus g of x. Or the area is, what is that, root 3 over 4. f of x minus g of x squared. Whoops. So if we're talking about the volumes, this is going to be the integral from a to b. And this is a constant, root 3 over 4, so root 3 over 4 can come outside. And this should just be f of x minus g of x all squared dx. So that's a bit of a tricky one. You just have to use Pythagoras' theorem there. Okay, I'll do this one in a different color here with the semicircle. Okay, so the area of the semicircle above in terms of f of x and g of x, well, the area of a full circle is pi r squared, right? So I guess this would have to be 1/2 pi r squared. And r is going to be 1/2 of f of x minus g of x. So the area is going to be 1/2 pi times the radius is going to be 1/2 f of x minus g of x. Or area is going to be, you know what? This is r squared. So that's going to be 1/2 pi. This is going to be 1/4 f of x minus g of x all squared. And those brackets don't have to be there. These ones. And so what we have here, this all mess here, is pi over 8. This is going to be pi over 8. Pi. And now the reason why we're doing this is because you're going to have questions later on that's going to ask you to do this. And you're going to be able to look back just to this. And it's going to, because you've done the work here already, so you're going to be able to just kind of fill in values for f of x and g of x. Okay? So this is going to be pi over 8 of f of x minus g of x squared. And of course this would be, the volume would be pi over 8 is the constant out there. The integral from a to b, f of x minus g of x squared dx. Alrighty?